So today, I want to talk about, I have a detail from the alternating series chapter that came up in the homework I'm going to talk about. So just a brief note on approximation. The alternating series test. And then I'm going to talk about sort of a recap of our existing tests. I'm going to start talking about how to choose what to do. So this is the sort of situation where you don't want to sit down in front of a problem and try every single thing you know every time, or there's just not going to be any time to get it done. Okay. So when we're testing a series, we like how to choose a convergence test. And this is leading into chapter 10.7. The homework on 10.7 will be next week, but this chapter is very similar to the chapter on integration, where they give you strategies for integration. Chapter 10.7 is called strategies for testing series. Same kind of idea. Okay. And so that's kind of what I want to do. Before I do that, if there are questions on the homework, I'd be happy to answer those. Anybody has any? Yep.
I just had a question. So the quiz that we took before that practice.
Yes.
The midterm will look similar.
Yes. Yes. That's like, so the idea of the quizzes is that gives me a library of question types that they may not map exactly on, but it's supposed to give you, hold on, I gotta turn the highlight on here. Since I can't see myself, which is frustrating.
So they'll be reasonable, not like crazy.
Yeah, I don't intend to give you guys, I mean, so the thing is that an exam in a class like this is going to consist of something like somewhere between 6 and 10 questions. You only have 50 minutes. I have a lot of different pieces I've got to test, right? So I can't give you completely insane questions. Where the insanity is going to come from, if it comes from anywhere, is the fact that you're going to have 7 series to look at, and you've got to pick which method works for which series, right? Because that's the way it will be presented. So that quiz plus the one that I haven't written yet that will come before it, plus the one I'm going to talk about tomorrow, that's like half the test right there. Is here's a pile of series, test them for convergence rigorously using the test that you know. So being able to discriminate when you look at a series or which approach you should take turns out to be the hard part. And then also remembering all the pieces, right? So I write exams by not letting people use calculators and by not letting people come up with notes, which I don't. The flip side is I can write exams that are reasonable. If I let people come in with note sheets, then I have to like take the gloves off and write an exam that works around the fact that everybody has every piece of, you know, what people come in with when they come in with note sheets is insane. Like, you know, the entire textbook, but with each page reduced to this big and a jeweler's loop on it so that they can eyeball, you know, every page of the book. It's just easier to restrict that. But yeah, the quizzes are going to construct sort of like a basic setup for how to approach the exam.
I was going to ask the quiz tomorrow is like the option, so we just take a class.
Yep. Yeah. I saw, again, I haven't got to the point. Attendance is getting better, but it would still, at this point, I would still be doing something like 20 practice makeup quizzes a week. And that's just too much for me to do. So I have 2 options at this point. I can do them in class and then talk to you about them, or I can put them online, in which I have to presume that everybody's just using all their notes and you know, the online stuff. And the problem with that is the point of the quizzes is not to evaluate you. The point of the quizzes is for you guys to be able to evaluate yourselves on how you're doing. So, you know, it doesn't really give me information about your grades if I put something up on Canvas. Then it's just I'm putting quizzes on to go through the motions of giving something a grade. So, yeah. Continuing on with ungraded quizzes. So structure of a quiz, contribute to what the midterm looks like, but not actually graded.
Is there anything on like fair?
So I haven't talked about anything to do. The only test that I actually went into detail on about how to use for estimation was the integral test, right? I'm going to begin today by talking about how the alternating series test estimation works, but I don't think I'm going to put that on an exam because I have so many other ideas. And basically, testing you on your ability to estimate things is, can you manipulate an inequality? And that's not really a calculus idea. So I'm not going to put an estimation problem on a test, right? Especially with no calculator. So I mean, it's a super important idea, but it's not productive for me to test what's going on in the class with that. Anything else? In fact, the one homework question that had an estimate in it on the alternating series thing, I didn't notice it was there, and I can't cut individual parts out of questions. So let me just open with that. So one of the questions on the homework for 11.5 said something like, find the number of terms you need to get below some error level. And so estimation with the alternate, it's actually really easy. So if you want to estimate with the alternating series test, the theorem says that the size of the error is smaller than the next term you would add or subtract. Okay, that's pretty easy. So if you had a series that looked like, I don't know, -1 to the n, 2 to the n over n squared times 3 to the n, or something like that, so it converges. If you had something like this, you can check that this converges by the alternating series test, and it said, oh, find n, so that the error is less than 1/1000, say, right? All the alternating series test convergence, or the estimation test does for the ASD, is to say, take that formula, put n+1 into it, and set it less than the error. That's it. Like the way you would do that, I mean, you wouldn't, but the way you would do it in this case is you would write 2 to the n+1 over n+1 squared, 3 to the n+1 is less than 1/1000, and then solve for n. Right? You can't actually do it in this problem because it's too hard, because it mixes polynomials and exponentials together. But that's the basic idea of estimating with the alternating series test. It's very straightforward. Your error is controlled by the next term you would have added or subtracted. Okay. Anything else? Okay, so let's talk a little bit about so let's talk a little bit about what the tests are. Okay, for example. So what do we know? And then and how do we approach a series? So I'm going to try to write this list in the order that I would use if I saw an arbitrary series and I wanted to know how to test it. Like, what should you check for? So there's no one process that's going to work for this, but it's good to have an idea of, from top to bottom, how do you approach a series question? So the most basic one, the book doesn't actually privilege us as much as I do. I think the very first thing you should do is just eyeball the series and see if the test for divergence works. So faced with a series, what do you do? Test convergence. I think the most important thing to do, step one, has got to be, you don't have to actually compute this. You just look and see if you believe it. Sometimes it won't be obvious, but check to see if the limit as n goes to infinity of an is not 0. Just eyeball it. You look at a series, and it looks like the terms, I guess the series we're considering here, now I'm thinking of a series with terms an, where they could be positive, they could be negative, I don't know. There's some formula for the terms, right? Check to see if the limit of the terms is not 0, because if it's not, you're just done. There's no other work to do. So if you get a series like, for example, I'm not going to give you one like this, but it's possible. Oh, that was worse being close. So somebody could give you something like this, right? It's like a ridiculously stupid series. You, in theory, you could write this into the form of a geometric series and check that the R is greater than 1 and say it diverges because it's a geometric series, right? You could do that. It's a geometric series. But if you see something where the terms obviously don't go to 0, just say it diverges by the test for divergence. limit as n goes to infinity of 3n is infinity. So the series diverges. It's also nice if you identify which test you use. So you could say test for divergence. I have a quick unrelated question for all of you out there who are potential material scientists and engineers of various kinds, which is, why on earth, heard me ask this question before, but nobody's ever answered it for me. Why do they manufacture chalk at the length of its harmonic frequency? Why? It's manufactured to be precisely as long as it needs to be to resonate harmonically. So it's built to squeak. So why? Why do they do that? Every piece of fresh chalk will do that. But if you snap it, now all of a sudden the wavelength, the frequency is bigger, that the material resonance frequency is shorter than what the chalk can sustain, so it doesn't vibrate. So my question is, why on earth do they do that? That's why we snap the chalk, if you don't know. Right? It changes the harmonic frequency of the chalk. So answer my question. That's my, unrelated to the class, but I've been very interested in this for years now because I hate that sound. It doesn't make any sense to me. Okay. So you've looked at a series, you've determined that the limit goes to 0, and so there's nothing you can conclude, right? If the limit as n goes to infinity of an is equal to 0, don't conclude the series converges. That is the single most common mistake people make in this section of the class. Just because the terms go to 0 does not mean the series converges. So what I would suggest second is look for known structure. You guys know two types of structured series. What are they? The ones you can just look at and immediately say if they converge or diverge. Geometric series and p-series, right? So if you look at a series and it looks like this, you can just say converges or diverges. Right? This is a structure you know. And I mean literally this. There is no test for convergence you need. You know what the classification of this series is, or you should. So p-series. And the geometric series. So no test needed because structurally we know when these series converge or diverge. Right. Now what? How do you identify things that look like p-series? No, that's how you test them. How would you describe what they look like? What do you look for? I mean, so I'm curious how you guys think about this. If you see a series on a page, what is it that makes you think, oh, this is going to be a comparison test? Or maybe you don't have a discriminating factor yet, yeah?
Polynomial on the bottom.
Okay, so polynomials running around in the top or in the bottom or top and bottom. Okay, so that's called a rational function. So a rational function is a polynomial divided by another polynomial. Does anybody know the name for functions like that that also involve square roots? Because those also work, right? So an example here might be an is equal to n squared plus 1 over n to the third plus 2n plus 1, right? That would be something that you might think, oh, that's a rational function. I know what to do with that. So I'm just curious if anybody knows the name of these guys. Series that look like something like n squared plus 2 over n to the fourth minus 2. It's not rational because there's this square root here. It's either called algebraic functions. Just need the vocabulary for that. The book is going to refer when you read chapter 10.7, if you read chapter 10.7. We'll refer to algebraic functions, but what it means is mixtures of polynomials and square roots. And so these things also you can use comparison and limit comparison on. So if you see structures where you have polynomials or functions like these expressions that involve powers and square roots, polynomial-like things, but there's square roots involved, you should think something in the comparison test family, either comparison or limit comparison. Okay. Now, of course, we have a more powerful tool available to us for many series, and you might be tempted to apply it to something like this, which is the ratio test, right? What's the problem with using a ratio test on anything you can compare to a p-series? Like, so you look at this and you say, oh, it looks like 1 over n, right? Which is going to diverge. So I'm just going to hit it with the ratio test. Because then I just have to know one test. I don't have to remember any of the comparisons. So you try to use the ratio test on that. What's going to happen? You're going to get 1. The limit will always be 1 with anything that behaves like a p-series. So don't fall into the trap of just saying, I don't need the comparison test because I've got the ratio test in my pocket. Okay? Anything that behaves like a p-series, the ratio test will fail. You need to use either the comparison or limit comparison test on anything that behaves like a p-series. Okay, so now we're starting to get down into the weeds. So we've already done test for divergence. We've already done special structures. We've already done the comparison tests. So what's left now, we're starting to get more exotic here, are the ratio test and the root test. How do I know to use one of these guys? Other than desperate last minute gamble, right? Which is certainly a strategy that can be applied to any of these questions. But how do you know?
You can use ratio as a factorial and then root, like when it's power n.
Okay, so the first thing is, if you see factorials, you should think ratio test. It's a big clue. You can't really do comparison with factorials because factorial is not generated by some function, and you're certainly not going to integrate a factorial. Okay, so you see a factorial, try the ratio test. If you see terms in this very special form, it's just an enormous red flag that this is a root test problem, right? If you can somehow collect everything together and get a single n on the outside, you're looking at a root test problem. Okay, so other places where you might think about the ratio test is anytime you have products of functions, mixed products. So what I mean by that is you've got polynomials and exponentials all jammed together. You might seriously think about using the ratio test. For example, something like if you had the sum from n equals 1 to infinity of 2 to the n over times n plus 1 over 3 to the n over n squared plus 1. This is what I mean by a mixed product. Polynomials and exponentials all together. You're not going to want to run a comparison with this, probably. Could, but typically these things are much faster if you think about them with the ratio test, because what will happen is exponentials will divide out, right? You make a fraction of terms, the exponentials will divide away, and you get a limit of polynomials. Okay, so factorials, mixed products. Then the mightiest tool of all, but the one that means it's one of the hardest to use. What have we left out? Oh, wait. We got one more to go. One more. Sorry, we're not quite there yet. I guess I put this underneath the ratio and the root test because often ratio and root test problems can be solved without it. If you look at a series and it's of this form, there's two candidates for looking at a series like this. The first is test it for absolute convergence with the ratio test. If that fails, you can't do that, then you have to check it with the alternating series test. So I put this before the alternating series test because when you're looking at an alternating series, absolute convergence will imply convergence, right? So I think you should try this first. Generally what my thought is. You don't have to, but it's my thought. So 5 would be if you have a series this form, the alternating series test. finally, the most powerful tool of all, integral test. Except to use the integral test, you have to be able to integrate the function. That's the problem. The integral test is awesome, but you have to be able to integrate the function. If you can integrate f of x, where a n is equal to f of n, then integral test. Normally, to make these things slightly challenging to deal with, what you're looking for is a U substitution. And I'm putting this at the bottom because it's easy to get sucked into the trap of trying to use the integral test on everything. Problem is there's very few of those functions that you're going to be able to integrate quickly. And a lot of the other tests work much faster. Okay. Okay, so that's your basic setup. What have I left out? Yeah. So over here, in another category, so this is number my professor hates me. Is telescoping series. The reason that is like listed in my professor hates me is because you usually have to do some sort of algebraic manipulation to see that it's a telescoping series. So way back at the beginning of the class, we talked about series that look like this. So the thing with this series is they told you telescoping series at the beginning, but then they never actually made you do it again after that. I mean, what is the obvious method for doing this now? Like if I gave you that series, yeah, in the background, maybe you remember that this is equal to 1 over n minus 1 over n plus 1. Maybe you remember that. That you can calculate this as a telescoping series, right? But how would you approach that if I just gave it to you on the page?
Comparison.
It's going to be compare. Yeah, compare. You don't even need limit comparison. You can use comparison here. Every single, I was okay, without telling me in words, every single person in here should form an opinion about whether or not that series converges or not. Okay. How many people think it diverges? You guys are awesome, or you're shy. So, this is one of the problems with asking people for these things. Yeah, it looks like 1 over n squared, which is a convergent T series, right? Since we've gone past the telescoping series, you may look at this and think, oh, that's a comparison. It's easy, right? You would never do the telescoping series unless somebody said you should calculate this as a telescoping series, and that's what I mean by putting it in my professor hates me. So I'd like you to do a bunch of algebra now, right? Please do some partial fractions for me. That's a question you want to get asked on the exam. Right? So telescoping series do show up. They're unlikely to show up independently, but if you notice something is telescoping, you're absolutely welcome to do it that way. If I give you a telescoping series question, it will be obvious that it telescopes. Like if I asked you something like, oh, please calculate the sum of 1 over n minus 2, even 2, I have to have the numbers be the same, right? 2 over n minus 2 over n plus 1. If I give it to you like this, well, now there's 2 terms stuck together. Doesn't make any sense to break it apart because each one individually diverges. So it looks like infinity minus infinity. If it was going to be telescoping, it would be obvious from the structure and probably in the prompt for the series, it would say, treat this as a telescoping series so that people didn't get lost in the weeds, right? So I make you a promise that if I give you a series I want you to do with telescoping methods, I will just tell you it telescopes. Show me how it works. Okay. So now, we're just going to write some questions now. We're not even going to solve them. You guys are just going to tell me how to do the question. I meant to bring my book and I don't have it, so I have to pull out my phone and do it. So I apologize. Current text. Modern teaching. assuming it loads. 6, 11, 7. Okay. So, example 1. I'm going to leave off the limits of integration, or the limits of integration, the series limits, just because it doesn't matter. You just assume that they all go to infinity. You know what? Take me 2 seconds to write that down. What does that do? Don't tell me, don't, you know what? We're not going to do any like series computation here, but I mean, what would you do with that? What's the idea? You see this series, right? The question of, so the point of all these questions is, you're sitting in an exam, that problem is sitting on the page. I would probably hit it with a test for divergence, because that was step 1, right? What does this limit do as n goes to infinity? Now remember, before you answer, since we're in calculus 3 now, instead of calculus 1 and 2, I'm always allowed to just do this. You want to circle lead terms, circle them up. What does this look like as n goes to infinity? Okay, what is the minimum amount of work I want to see? Divergence, and you would say that diverges by test for divergence. So you don't want to get, again, if you don't notice that, it's easy to get pulled into a comparison testing, which will take a lot more time. All right, example 2. How about this guy? You don't have to tell me if it converges or not. That's not the point, right? I'm not expecting you to apply the test right now. The most important part of this part of the process is identifying which test to apply. So what do I do with this and why? Why ratio? The factorial. So we're going to be looking at the limit as n goes to infinity of 2 to the k plus 1 over k plus 1 factorial over 2 to the k over k factorial. Now I'm going to give you another test here. What would need to be true for this about that limit for this series to converge? This will converge if L is less than 1. Does 0 matter in this one? What if 0 came out? Is that good, or is that okay, or is it not okay? It's okay in this case, right? Ratio test, if you got 0, everything is still convergent. Okay? That's the only condition. All right. How about this one? Right, I'll go down. Sort of gave the game away there tonight. I have to save it and come back. All right. How about okay, so here's kind of a trickier one. What if I told you I had a series that looked like 1 over 3 plus 1 times 2 over 3 times 5 plus 1 times 2 times 3 over 3 times 5 times 7 plus, and so on like that. Now in sigma notation, what you'd be looking at is something like this. N equals 1 to infinity of 1 up to, so I guess it's n factorial on top, and on bottom, you have a pattern that starts at 3, ends at 3n plus 1. That's tricky, right? There's no factorial there. I mean, where'd that go? What do you think? I see you look at me. Is it 2n plus 1? 2n, oh yeah. Yeah. Well, that's what you're thinking. Thank you for helping me fix it. How do I do it? Time's burning. You're on the exam, just sitting there looking at it. You gotta do something. I'm watching you sweat or sit in your desk like all the things people do when they're nervous. Got factorial in it. Yep. So you can try that, but the problem is that this has a factorial in it, but this has the same number of terms that that does, because you're multiplying starting at 3 and going to the n. So if this has n terms in it, so does this.
Oh.
Right? So orders of growth aren't going to help you because this is sort of a factorial-like object. It's not quite factorial because it skips the middle term, but it grows like a factorial does. So when you're looking at kind of an abstract pile of products like this, what this means to me is probably people have really dug into the 11.6 homework yet. But this is what you would think of as a mixed product. So you should think about a question like this, even if there was no factorial here, even if somebody wrote the question like this, you should think about this as something the ratio test would work on. Because if you went one further number in the sequence, you're going to get the same term, but with an n+1 right here and a 2n+3 right here. Right? So you're still going to get nice algebraic cancellation. If you compute something like this, the very first thing you should try when you've got these piles of products is the ratio test, right? Piles of products, ratio test, because products cancel when you take fractions. The idea is that if you wrote this with a ratio test, the algebra that you're looking at is like this: 1, 2, 3, 4, 5 up to n plus 1 divided by 3, 5, 7 up to, thank you for the correction, 2n plus 3, and then flipped upside down on top of it is 2, 3 up to n and 3, 5, 7 up to 2n plus 1. Notice a ton of stuff cancels in this function, a ton. All of this cancels with all of that and leaves an n plus 1 behind. All of this cancels with all of this except for the last thing in the pattern, which is the 2n plus 3. When the dust clears after you do the ratio test on this, you're left with something that looks like 2n plus 1 times n plus 1 over 2n plus 3. That limit is easy to compute. I even 2n plus 1. Right. 2n plus 1 is in this list, right? It's the previous term in the list. Since it's the previous odd number. So the idea is if you see incredibly complicated products, use the ratio test. If you're curious, like where, this looks like some sort of like horrendous mathematical abstraction that we came up to make these problems hard. Weird series like this come up all the time in things involving like quantum operations. Now, you get all kinds of weird series with terms that are stacked up out of these products. All right, next. What?
You take the e value, you get n squared. That's like
Yes.
u sub.
It's a u substitution, right? This one looks like a u sub. If you notice it looks like a u sub, u would be equal to x minus x squared, say, whatever it happens to be. That looks like an integral test. Now, you do one. Say that you actually compute this. And you end up with the number, I don't know what number you're going to end up with if you do it this way. You end up with some L. Take that limit, some L comes out. Maybe it's 1. I don't know, whatever it happens to be. What condition do we get on L for this series to converge? In the integral test. The integral test. L had better be greater than Z. It has to be positive this time, right? The integral test doesn't make any sense if it's equal to 0. Something would have been really wrong if that happened. I mean, if you're integrating a positive function, you get 0 out. Actually, maybe it does. Is it okay at 0? The integral test? Generally, you're not going to get 0 because you're integrating a positive function. So I guess the idea here is it's okay, but you should really check your math. If you get 0 out of an integral like this, you did something wrong, right? You're not going to integrate the area under a graph and get nothing. I mean, if you do, you could, but it's unlikely. So what are you looking for on the other side? Less than 1, less than infinity. So here, unlike in the ratio test, what we care about in this case is the limit exists and is finite. If the area underneath the curve adds up to something, then everything is okay. This is another hard part of this, is keeping track of which conditions go with which tests. Because we have one more to go. Sorry, I stopped numbering the exercise, the example. Who are we on? Example 5. Sum from m equals 1 to infinity, say, oh, let's see, what's the next one here? Right, how about, like that. Okay, so if you think in comparison, what are you going to compare it to? Because remember, that anything in the comparison family, you have to have something to compare it with, right? What are you going to compare it to?
Whatever the powers in the fun do.
Well, I don't want to do it. Somebody tell me what this compares to. Yes. Remember that the idea, again, because we're in calculus 3, when you're looking at something like this and you want something to compare to, it's okay to start circling lead terms, right? So even though there's a square root up here, the behavior of the numerator is controlled by this end of the third. And the denominator is controlled by this 3n cubed. And so in the long run, this thing is going to start looking like this. Right? Eventually, that's what will control what's going on in this series. So it's okay to circle lead terms underneath a square root like this. What does that look like when you simplify this? Remember, root is just a half power, right? So it's n to the 3 halves over n to the third. Is 1 over 3, n to the 3 halves. Now, this idea right here, the long-term behavior, that is certainly your candidate for comparison. But suppose that you decide, I'm going to do comparison tests. I don't want to compute a limit. I'm going to do a comparison test. What are you being asked to do? Well, this is convergent, and you suspect that this is also convergent, right? This is a convergent piece. So you say, oh, that must also converge. So the inequality that must be true to show that this is true by the comparison test is this one. I don't know about you. I want nothing to do with that inequality. I mean, the first move is to square both sides, which means having to multiply out this enormous polynomial on the bottom, right? We've got to get rid of the square root if we want to work on this algebraically. So you do this, and then you realize this is too much work. And also maybe not true. So your next move should be to do the limit comparison test with the same comparison. So if you don't have an immediately obvious inequality in the right direction, don't use the comparison test. The process should be the same. I'm going to compare this to this. Do I really want an inequality involving these two objects? And the answer is no, I don't want to do that kind of algebra. So instead, consider the limit comparison test. This means that you're looking at the limits. N goes to infinity of the absolute value of an over bn. One of the series over the other one. Okay, so a limit comes out of this one. What does this one need to have? What condition that has to exist on this limit for the limit comparison test to give you information? It's got to be strictly bigger than 0. Strictly, I mean, yeah, in our class, we don't think about infinity as being a value contained, but yes, right? It has to be a finite number that exists, but also not 0, because if you turned this upside down, 0 would turn into infinity. So in the limit comparison test, you can't be 0. 0 doesn't tell you anything. Yep.
Is there inequality? Don't you do the other way?
Oh, yeah, because it's convergent. Yeah, sorry, you're right. You would need to show it in that direction. Absolutely. I meant to write it the other way. Yeah, I mean, for the comparison test, you know this converges as a convergent T-series, and so you need this to be, in order for this to give you any information, it has to be less than a convergent series. The problem with doing an inequality like this is you're going to end up with cubes in inequality, which means there's going to be places where the inequality holds and places where it doesn't. If you guys remember in the dark past, there was probably a time in pre-calculus where you dealt with quadratic inequalities. And if you remember quadratic inequalities, that usually involves factoring things and building a sign table and checking when things are positive or negative. You don't want to do that, and you don't have to because you have the limit comparison test at your disposal. Okay. All right. How about this one? I'm going to give you one that has like 3 different ways that you can hit it. This is example 6. -1 to the n plus 2, 2 to the n minus 2, 3 to the 3 minus n. In fact, let's make things better. 3 to the 3 minus 2n. Man, just a giant pile of nonsense. So there's at least 3 ways to attack that series, depending on how you're thinking about it. At least 3. So what's your first thought?
Absolutely.
Okay, so you want to test it with like a ratio test. Maybe, right? Test it for absolute convergence. Test for absolute convergence. So normally, now, okay, you're going to do this with a root test or a ratio test?
Probably. Don't know yet.
So you might be able to sort this out so you can pull all the stuff with the nth power and yank the nth power all the way out. So if you did that, I think you'd end up with something of this form. So if you took the absolute value, then you have a series that looked like 27 over 4 times 2 over 3 squared to the n. Which would mean that you could rewrite this as something like 27 over 4 times the sum. That would be a way you could hit it with a root test, right? If you're going to hit it with a root test, you absolutely need to get an nth power pulled out the side so you can apply the root test to it. Of course, by restructuring this thing algebraically, I may have suggested one of the other approaches to this question. This is a geometric series, right? The fact that I could rewrite the series in this way suggests this is geometric. So you could also think about this as a geometric series. Because the extra 1/4 that's hiding inside here and the extra 27 that's in here don't actually affect the convergence of this series. Right? If you think about this as being -1 to the n plus 2 times 2 to the n times 2 to the minus 2 times 3 to the 3rd times 3 squared to the n, to the minus n. That right there is probably enough to show you that this is a geometric series. That's like you yank the things apart so you can isolate the exponents. Typical trick when you've got mixtures of powers. But when you see bases raised to powers that are n's, even if they're mixed in with +1s and -2s, it still could very well be the case it's a geometric series. Okay, now suppose you didn't realize either one of those things. You didn't realize that, you know, you hit it with the root test, you just naively look at this thing and say, I don't know, it's a product of a bunch of things. What do we do with products of a bunch of things? Hit it with the ratio test, right? If you hit this with the ratio test, you're going to take this term and like add 1 to all the n's and then divide by the previous one. So you'll be looking at this limit. The minus ones don't count. Minus 1 to the n plus 3, 2 to the n minus 1, 3 to the, okay, so n plus 1 goes in and turns into negative 2, 1 minus 2n. So minus 1 to the n plus 2, 2 to the n minus 2, 2 to the 3 minus 2n. And that's just simple algebra. You just subtract exponents. Doesn't look like simple algebra, but it is, right? Minus ones don't count because you're an absolute value. N minus 1 over n minus 2, or 2 to the n minus 1 over 2 to the n minus 2 is just 2. If I take 3 to the 1 minus 2n, I subtract 3 to the 3 minus 2n from it, I end up with 3 squared. So if you do this with a ratio test, it's even easier. It looks harder at the beginning, but the thing you get is dead easy to interpret. There's not even a limit to take. It's constant. Right? So again, most of these questions are going to have multiple approaches, but any way you think about this is a correct approach. You think about pulling out all these n's because the root test exists, or you recognize that you've got a bunch of bases to n's and that you've seen enough of these in the geometric series section that it's an obvious manipulation into this form, or you just blindly apply the ratio test because it was a product of a bunch of crap. All of it works. Okay. So one of the hardest parts about doing these things is not just picking a test, but trying a different one if you hit a roadblock taking a test, right? You try one of these tests, it doesn't work, you can't stop, you have to try again. So in that way, this is exactly parallel to the stuff that we did on the integral test. Okay. So what I want you to do is, I just want you to practice these things. So the absolute best thing you can do right now, if you're looking at these and you don't know how to translate the series on the page to your test of them, is to just go to the actual book. I'll post this page on the Canvas page. I'm going to go to the book. I'm going to strip out the exercises from section 11.7, which is not just the Canvas, the web assignment, but the actual textbook version. And I'll post them up there. Just try to say what test you would use on each series. Even if you don't compute it all the way through, identify what your strategy would be and have a reason why you pick each one. So I don't want to lose anybody. I'm really emphasizing this because the reason this class has the reputation it does is in large part because of this part of this exam. Everything that comes after the series section is regular calculus. This is a brand new idea for most people. There's a billion moving pieces and it's very easy to get lost. Okay, so practice and repetition are where it's at. So what we'll do tomorrow after the quiz is we'll do another one where I have maybe I'll just bring that in. I'll print a copy of all those exercise pages. I think most people don't have physical books. I'll just give you a copy of the exercises from the 11th. Let's work through them. Okay, so quiz tomorrow, group problem day, and then after we get through that, we'll move on to power series, which is maybe the most important idea in undergraduate calculus. So thanks for your attention, and I'll see you tomorrow. See you guys.